Hello everyone, this is Ashwin here. In this video, we are going to see about how to build a snake game using reinforcement learning, and we are going to use QTable in order to train our agent. So this blue color snake is the trained one. As you can able to see, it can able to get the mouse quickly, and the score is also in positive. And this is the snake having random actions. So it will be randomly moving around the space, and it will be just getting the mice randomly. So this is the trained one and this is the random one, and we are going to build the whole training and testing in this video. So let's see that. So this is the code we are having. So this code I got it from hackathon. So they have asked us to train a agent that can compete with another agent. So usually it will be like two bots compete against each other. So we are going to do that, and I'm also going to explain what is there in the environment. Like it is a custom environment, and we are going to train the agent using the custom environment. And don't worry, you can get this code from my GitHub repo. I will put the link in the description, and let's dive into the project. So first I am going to explain a few things. This is the important modules we have to install, that is Jim and Quince and Ray, and these are all some common stuff. You just run it, and after that this is the import modules. So we are going to import all the Jim modules, so the environment, discrete. So this nqueens is like a nqueens problem. You know that queens will be placed in a non-intersecting way. So similar to that, we are going to place the mice in a non-intersecting way, like in the random order. And these are all some other common modules, like this is for visualization and this is for normal operations. And if you are using Google Colab, means this will be patches you want to use. Like if you want to use OpenCV and display the images, means you can use this. So if you are doing it in the local, so you don't need to worry about that. And that's about the import modules. Let's run this. So this is the environment we are going to use. I'm going to explain like what is the function gonna do. We don't have to like dig deep into the code and explain line by line. So this is like a big code. As you can able to see, this will take a longer time to explain. You can use this kind of custom environment, or you can use some existing environment for the training purposes. I'm going to just show you the training process. So before that, I have like faced an error for Google Colab. So I'll just comment this for now, and this, yeah, it ran. So now in the custom environment, first we have the foot position. So it will be just placing the foods uniformly. So it's already commented, so you can clearly see. And while returning, will be returning the food locations that is spatially distributed. And these three are initialization. So this is for initializing the agent. So we'll be placing the agent at a random location. So this is the initial state, and the agent have some head. So I'll show you the head right now in the example. So this is the head. Head is pointing toward which direction? Head is pointing toward east. Like that, it's storing the state of the head. And here we have the score. Initially it will be 0. And this is the state. So this is just a random position you will be placing the snake initially, and this is just a velocity. And init image means for those snake we have like a image, that is a PNG file. We'll be loading that, and you can get those files in the GitHub repo. So and the next we have the constructor, and this is the initialization. So we will be initializing everything, the rewards, and what is the game length, and what is the action space. So currently we have actions like left, forward, and right. We just have 3 actions, not like multiple actions like go diagonal or go back. So we have only 3 actions, so that we have to remember, and using these actions we have to code it or train it accordingly. So all the other things, so you can clearly see this is our initialization. These are all initialization again, and everything will be done. So in the moment, based on the action, it will do the movement. So currently it's just getting the states of the agent, and after that, based on the action, it will check whether it is legal action or not, or it is out of bound. Based on that, it will just move the array. So these are the whole thing, and finally we will be returning the changed or modified the states of that particular agent. And this is for calculating the reward. So if it's not a legal action, means we'll be having the illegal action, that is -2. I will show you the reward section later, like what are the rewards we are giving. And this is for if we eat the mice, that is the food. And what happens if we eat the food? So we have to like randomly respawn that mice in some other position. So that is the code for that. And this is for the normal movement rewards, like if we just move and didn't get any reward. So for that we will be having some negative reward for this moment. Like if we make unnecessary moves, means it's not much efficient. So that's why it's a negative reward. If we reach the food, means it will be a positive reward. So I will explain the whole configuration later, as I said. And this is the step. Step means it will do the action for agent A and agent B. So here we are going to calculate the reward for both the agents. Suppose if the two agents collided, means this will be calculating what happens. Like if the snake has higher reward, means it will be having using this formula, we'll be allocating reward to that snake. So here you can see if the score is higher for agent A, we'll be having some kind of a positive reward, and for the other agent that have lesser score, will be having a negative reward. So that is also another reward function we are having. And here we are just updating the history and states again, and we are also checking whether the game is ended or not. This is like a complete episode, and game length is like steps. So here rotation means we are just rotating the direction of the head. So based on the action we are giving, we are just rotating the head. And this is render function. This is useful for visualizing the whole states, like while doing the actions. So that is common for reinforcement learning. And this is encode. We are just encoding the states. It's like a one-hot encoding. So you can use this encoding as well. I'm going to use some simple encoding, that is just the index values of that whole matrix. And reset means it will reset everything, the game length, reward, the agents, everything will be resetted, and it will start a new game. So that's it about the whole custom environment. So you can go through using the commands itself. It is easier. So this is the configuration. Configuration n is like the size of the whole matrix, that is 8. Rewards, we are having food as positive reward, movement as -1, illegal means -2, that is out of bounds. And here the game length. So currently we are having 100. So we can also increase the game length for training. Let's say we can go for 1000. So that can be done. So let's run both of these cells. So it ran, and this is for the testing purpose. So after you have trained the model or the Q table, we can test it here. So we have evaluate A. So we'll be returning the action. For evaluate B also, we'll be returning an action. So based on that, we can visualize the whole episode. And we'll be initializing that later. I will show you at the end. It will just create a video that I have shown at the starting point of the video. So we will see these things later. Now let's get into the action. So we will leave some space. Now here we'll be having configuration. So we'll be initializing a few variables here. So first we have start Q table equals, initially it is none, and size, that is n here. So size equals config of n. This will be in string. So this will get this 8 here and store it in size. Next we'll be having a food reward. food underscore reward, that will be 4. I'll just mention as it is. So anyway, it's like a default one. And after that, we can have epsilon. So this is for taking some random actions. So epsilon equals 0.9 initially, and we'll be having decay. So EPS decay equals 0.9998. So we'll be like slowly reducing. And after that, num episodes equals, I'm going to run it for, at least you have to run it for 50k with 1000 time steps. So that is that. And I think you don't need to mention any time steps here, so we will just leave that. And player bot equals a. So this is just defining which agent we are going to train. And after that, we can have learning rate equals 0.1. So this will be fastly updated. Discount equals 0.95. So this is for updating the Qtable formula. So I will show the Qtable or how the updation happens. So this is just the configuration. Let's run this. Now that's done. So now we are going to initialize the Qtable. So initialize the Qtable. So now if start Qtable, it's having start Qtable is none. Okay, I mistakenly ran it. Let's run pass. Yeah. Now before that, in the else part, so if you already have a Qtable, means it will go to the else part. So you just have to specify the file name here. So I'll say print loading Qtable and with open of start Qtable comma read binary as f. Now here Qtable equals pickle dot load f. So you have to import pickle for this. So I'll just import it quickly. Import pickle. Okay, that's done. So if you already have the Qtable, means it will load this quickly. And if you don't have one, so we will creating Qtable. Now Qtable equals a hash map. So we are going to define the observation or input states. So based on the particular state, what action needs to be taken. So those are the values are in the Qtable. I will show you a sample representation after defining one function. So it will be easier for you. Now we are going to initialize the Qtable. So for I in range of minus size plus 1 comma size. Now similarly we have to do it for 4 times. We are going to have like 4 coordinates. So just copy it and paste it 4 times. You can have this as I, J, K, L. So these are all coordinates. And lastly, we are going to have a state for the head. So for m in range of 4, we have like 4 possible directions. That's why. So Qtable of inside a tuple, again inside it, we'll be having the coordinates I and j, and this is k comma l. So the starting coordinates is for the food, like the nearest food from our agent, and this is the enemy coordinates, like what is the coordinates between the enemy and us. And finally we'll be having the head, that is m, equals np dot random dot uniform of -5 comma 0 for I in range of 3. So this is the action space, like we have 3 possible actions. That's why I'm just specifying the action space here. So it will be having 3 values. You can also, maybe we can run this in a separate cell so you can understand how the values are there. So like this, it will just randomly initialize 3 values. So this is action 0, action 1 and action 2, left, forward and right. So like that, we are just initializing random values, and after that we will be updating these values in the training. And these are the input states. So this is the foot coordinates, this is the enemy player coordinates, this is the head of our agent. So that is initializing the queue table. Currently it is none. Let's initialize it. So it is created the queue table. Now we are going to create a function for getting the coordinates or input states. Create function to get input states. So I will say def get input states of environment and player. Player equals, by default it is A. If you want to change it to B, means you can just pass it as a parameter. Now player A equals, so here player A will be n dot agent A, and player B will be n dot agent B. So that is done. And here we are going to say if player not equals A, then it is B. So we are going to swap the players. So player A comma player B equals player B comma player A. So anyway, if we didn't swap, means this operations will be same. So all the operations remains the same. So if it's agent B, means we are just going to change those coordinates. That's it. So rest of the operations will remain the same. Now we are going to get the food. So I'll say foods equals n dot live underscore food spawn underscore space. So this will give you the index of the food location, and head equals player A of head. So this will give the head for player A, and after that we are going to calculate the player coordinates from the enemy. So I will call it as enemy coord equals, so we are going to have x and y, right? So I can have player A of state of 0 minus the same but with player B. So that is done. This is player B, and similarly we will getting the same for index 1. So this will be y index. So this will get the enemy coordinates, and after that I'm going to have nearest food. So nearest food means we are going to get the coordinates for the food nearest to the agent. So initially it will be none, and after that we are going to have some distance equals, I will initialize it as 100, so that's not an issue. Now we are going to iterate the food. So for food in foods temp distance equals, I'm going to get the distance using Euclidean distance. So np dot lin arg dot norm, that will be player a minus food, and I can have absolute. Anyway, it will be absolute, so not an issue. Now if temp distance is less than the current distance we are having, we are going to update it. So distance will be updated to temp distance, and nearest food equals the food coordinates. So that is done. So I will also have some comments, so it will be easier. Swap coordinates for another agent, and getting states for head and foods, calculating relative coordinates for enemy, and calculating relative coordinates for the food. So here we are going to calculate, I'll call it as food. Okay, food coord equals, again we are going to have the same thing. Instead of player B, we are going to have food. So I'll just copy this, paste it. So here instead of player B of state, we are going to have food, and here player state of 1 minus again food of 1. Finally we are going to returning the state. Return, first we are going to return food coord, and after that enemy coord, finally head. Run this. Now we can get some sample input, like initially pass the environment, we don't need to pass the player. Run this. Okay, has no lives food spawn. Okay, I just made a mistake. Food spawn. Run this. Okay, this will be the state. Again run this. Okay, now you can see the coordinates, right? So this is the relative coordinates for the food, and this is for the enemy, and this is for the head. So this is like an initial state. Let's say if you are having B coordinates, run this. So currently based on this agent, the relative coordinates are changing for food, and this is also not changed because we are just calculating the difference between two players. So that's it. Okay, that's done. I guess I'll just leave this here for an example. Example states. So while calculating a Q table, what it does means, for this combination of values, what is the best possible action? So that's what we are initializing in this Q table hash map. So for this possible coordinates, what is the possible action? We'll be getting that highest probable action from here. So that's done. Let's jump into the training part now. training the agent using Q learning. Okay, now we are going to type a lot of stuff. Let's start it now. So first we are going to have episode rewards. So each episode we are going to have some rewards. I'm going to store it in a list. Now for episode in range of num episodes, first initially the episode reward will be 0, not rewards, reward. This is for the single episode, so it will be 0. And after that we are going to get into the time steps. So for I in range of, I think we do have to define the number of time steps. So num underscore time steps. I'll just initialize it quickly. We are going to have 1000, right? So here I'm going to have it as config of game length, game underscore length, and this. Now here, yeah, after inside the time steps we are going to get the coordinates. So observation equals get input states of environment, and a player bot you can pass because we have initialized it. Do we initialize? Okay, player bot. This can be in capital. Player bot. So why I'm initializing some variables in all caps means that variables is not like mutable. So it will be easily differentiated. So that's why just passing the player bot. Now we are going to have the action. So for action we are going to have a dictionary. So because we have to pass two actions, one for one agent and another one for another agent, so will be two actions for each of those agents. So this will be a dictionary. Now here we are going to have get action. So if np dot random, so this will generate a value that is in the range of 0 to 1. If that is greater than epsilon, then we can take the action from the Q table. So this is for action A. So this represents action for the agent A. If you are doing it for B, means you have to change this. Now here np dot argmax of Q table of the observation. So that is the input state. Based on the state, it will give you the best probable action. So if this is not satisfies, means we'll be taking some random action. So copy this and paste this, and here I'll say take a random action. So here I will take a random action. To do that, n dot action space dot sample. So this will give you the actions that are available like in a random manner. So that's done. So this will take best action for observation. Okay, now we are going to take the action for another agent. So I will have action of action B equals n dot action space dot sample. So for the other agent I will always take a random action. And next we are going to calculate the reward. So we will be having reward A, reward B, info, done, and info. This is like a common returning parameter, but Here we are having reward for another agent, but we don't need to use this. We just need this action A. So n dot step pass the action, that is this dictionary, and after getting the reward, here we are going to do the calculation. Let's do the calculation. So now we are going to have a new observation after taking an action. So that new observation will be new observation equals get input states of environment dot player bot, because all the, if you take an step means it will automatically go to a new state. So currently I'm just getting the current state, getting the new state after an action. After that we are going to have max future q equals np dot max of q table of the new observation and current q equals q table of observation of the action we have taken. So that will be action of action A. So this will get the maximum q, that is for the new observation, and this will get the current value of the q. So that's done. So this is useful for the calculation. That's why now here if reward A equals food reward, or you can also have greater than or equal to, because if you collide means you may get a chance to get higher reward. So for that I'm just having greater than or equal to, then your new q equals the food reward, else q table formula. So this is the formula I was talking about. So this is the q table formula we are going to use. So the new q will be, like if it's negative reward means we'll be updating that new q. So that will be 1 minus learning rate multiplies the current q plus learning rate multiplies reward A plus discount multiplies max future q. So you can get this formula from the internet also. So I'm just converted that formula into a Python evaluation or function. So this will be updating that. After that we are going to update it inside the q table. So that will be q table of observation of that particular action. So that particular action equals new q. So this will be update the q table. That's done. Okay, now after that we are going to add that reward into episode reward plus equals reward A, and that concludes our whole time step. We'll be just having this inside this for loop. When it's completed, if episode modulus 1000 equals 0, like for every 1000 steps we'll be displaying the episode reward. So for that, print format of episode equals the episode. So this will represent which episode we are in, and colon will be having episode reward, and after that if again episode modulus some 20,000, like after 20,000 episodes we are going to store our Q table. So for that, with open of f of Q table and the episode, which episode we are in, dot pickle, comma, write binary as f pickle dot dump of Q table and f. So what we are doing is storing the Q table after every 2000 episode. So I'll just say saving the Q table. So that's done. And after this, we are going to have episode rewards dot append episode reward. So we are just appending to the episode rewards list, and we are going to update the epsilon. So epsilon multiplies equals EPSDK. So this variable have like smaller case. This means the value will get updated. That's why we are having it in smaller case. And I'm just going to paste this here. And after that, this is for printing purpose. And if everything is completed, we're going to print average rewards. Average episode rewards equals np dot mean of episode rewards. So this will give you the average episode rewards. So this is our whole training. I guess this is a lot for you. I'll just go through in a simple manner. So first we are just having the episode reward as 0, and we are just getting the input states for our player. And after that, based on the epsilon or the randomness here, we are going to get the best probable action from the Q table, or else we will be taking the random action. So in the initial state, our epsilon value will be higher. So we'll be mostly taking random state. While updating the epsilon, slowly it will be getting reduced. So after some periods of time, and we'll be getting most of the actions from our Q table, that is in the later part of the training. So after that, we are just getting a random action for agent B. So get random action for agent B. And after that, we are just taking a step. And we are just doing the calculation for updating our Q values and update that into the Q table. And this is just the formula for the Q learning. And we are just adding that into the episode reward. If you are training it for agent B, means we'll be having to change these actions into like action B or action B like this. You have to change it for a few areas. And we are just updating that episode reward and updating the epsilon value, like it will be slowly decreasing, that is the epsilon decay. And this will just show you the progress, and this will just save the states after some 20,000 episodes. So that's it. Let's run it once with the episode as 10, so we can see whether it is running properly or not. Okay, we are getting some error. Okay, now okay, currently we are having like 1118, so that is a large number. So this will be just slowly decreasing. This will take a longer time for you guys because we are having a episode number as almost 50,000. This will definitely take some longer time for you to train. So yeah, we will just wait for a while. So this training could take some time, so I'll just minimize it. I already trained this, so you can also load this directly. So with, we already have some loading function before. We'll just copy this and paste it here. So for the Q table, we're going to load it. I already have some best Q table, best underscore Q table dot pickle. So this is I have trained for 100,000 episodes. So this will be easier. If you want to load it, means you can just load it directly. Currently the training is going on. It will definitely take some longer time. So yeah, in the meantime we will create some code in order to check how the agent is working with the random agent. So here I can have testing with random agent. So for I in range of 5, we're just going to have like 5 episodes. Done equals false, and environment dot reset. We're just resetting the environment. While not done, we're going to have our observation similarly. So observation equals get input states of environment comma player bot comma. So action equals action of action A. We are going to get it from the Q table, that is np.orgmax of Q table of observation, that is this. And similarly for agent B, action B equals environment dot action space dot sample. So this will take a random action, and after that we will take a step. So here we will be getting reward A comma reward B comma done comma info equals environment dot step of action. And after that it will do it for some time. You can also have a rendering function if you want to see it, but I'm going to use the rendering function in this inferencer. So we will see that video later. Now if the while loop breaks, means we'll be out of that. So we'll be printing print info. You can also have like if done equals true, print info. So that's that. So we can test out our agent performance like for 5 times, and we can see the score here. So currently you can see it, right? Initially our agent reward is like minus 1100. Currently if you go down, we are getting rewards around minus 800 or minus 900. So slowly it will take some time. If you progress around more than 20,000 episodes, we'll be getting some positive reward, and after that we'll be getting some good positive rewards. I will show it here. I'll just stop this. You can run it if you want, like for your project. So I'll just stop this and I'll just load my trained Q table. So load completely trained Q table. This will be trained with 100,000 episodes. Run this. This has been loaded. Now let's run this one. So this is get input states. So for this I am just running this whole training in a separate cloud machine, because I don't want to run my machine for a long time. So in the training you just need to add one more thing in the code snippet, that is n.reset. So every time if you are starting the episode means you have to reset everything, so it will be like a new game. So I'll also have reset the environment for fresh start. So that's that. And we can also like remove this dictionary. We can have it the initialization itself, because it's not necessary to keep on initializing. So that's it. So if you run it means it will run normally. I will show you my other notebook. So this is my cloud notebook. So it is actually running. So you can see the rewards. So this is the episode reward. Initially it's in the range of like -700 for 1000 time steps. So over the period of time, after like 7,000 episodes, we are getting some positive rewards, and you can able to see after like 15,000 we are getting around 300, and we have a maximum reward of around 403. So these are the average rewards we are getting, and it's still training. So I'm just training for a long time. I'm just going to use this weights, or I'm going to use this Q table for our test execution. So the average reward is around, you can able to see it's around 350 to 400. That is the range. Now let's switch back to the notebook. So now here you can see every 20,000 episodes it will save the Q table. So you will have a backup, and here you can save your last Q table, that is called like best Q table. You can save it. I'm not going to run it now. So now we can load the Q table. So now the Q table is loaded. So before running this testing with the random agent, you have to like change this one. So because I have used it like this, only food, so that is wrong. So you have to use the nearest food in order to get the optimized coordinates. So you can able to get the nearest food first. So it will take less time, and it will also cover less distance. So you can minimize the number of steps. So change that back. So run this function, and after that train the whole agent again. So I have trained it separately, and I'm going to use the same best Q table.pickle. So this is the training I have done for 50,000 episodes. And after that you can run this testing with random agents for 5 episodes. Let's run this one. Now you can see our agent A having a score of around 367. It's ranging from 300 to 400. So the highest is like 392. And for agent B, that is using random actions, it's having -1000. So that is worst score you can get. So that is using random actions. If you train the agent properly means you will be getting this higher score. So that is, you can observe with this comparing with training and actual agent. So that's done. Next, so this is the code for doing some inference. So after you have trained some model for agent A and agent B, you can make that agents to compete against each other. So currently the game length is like 100, and remaining everything will be same. You just have to fill this evaluate A function and evaluate B function for our competition. So we will just fill those function. So this function, or the whole class name is called runner. So we will initialize the class. So we already have the Q table, right? So this is the Q table. So I'll just pass it as like model A, And for model B, I'll just pass it as none. And what else we have to pass? Some checkpoint. That is also we will just pass it as null. So for evaluate B, I'll just use some random actions. So action underscore B equals self dot environment dot action space dot sample. So this will give you some random actions. And for action A, we have to do this. So first we have to get the observation. So get the observation, and here don't forget to change this. So this is self dot environment. So it will call this environment. So this is like a separate environment for you guys. If you don't do this means you will definitely face an error or your model won't perform properly. And after getting the observation, we will do np.argmax of action. So again copy this and paste this here. Remove this, instead of that action A, np.argmax of q table of observation. So this is done. So here we have to use self.model A instead of q table because we are passing it here. So sorry, this is here. So that's done, and we will decrease the number of runs, that is to 100. So that is enough for us because it will take a long time if we have number of runs to 1000. So for now we will just have it as 100, and let's initialize this class. And now contest equals runner of, first we will pass the q table. So that is our trained model. So that is for agent A, and for second agent I don't have anything, so I'll just pass it as none. And for the third one is checkpoint. So checkpoint means it will store your files on your checkpoint. So we'll just pass it as empty string. So it will store the video in the same folder where you are running this code. And now contest.arena. So this contest.arena will try to run everything. So it will run it for like 100 times, and it will return the winner. So that is our result. And apart from that, we will also get the video for the 100th episode. So that's done. Let's run this. So this will take some time, and after that we will get a clear winner of who wins the game. And we can also see some clear visualization of this whole game, like at least for a single game, in a video that I have shown at the start of the video. So let's wait for it. Okay, now we have a clear winner, that is player A, that is our trained agent, won all the episode, and player B didn't even win a single one. So for visualization, let's see the video. So this is the video. I think I have run it for that 1000 times. We can ignore this. We will just concentrate on this one. So this is our agent, that is agent A. You can clearly see how it's going to the nearest mice, and this agent is like randomly moving. Now it's trying to get all the mice nearby as possible. And you can see it's dynamically moving, and we are getting the positive score, whereas the other agent having a negative score. So this is how it works. Similarly, you can use the same walkthrough or the whole code structure for any other project. So that will be very helpful for you, and you can just do your customization, and you can add your own logic or the input states. So like this you can do so many things. And that's it guys, this is the whole tutorial. So I didn't like cover the custom environment because it's like huge code. I definitely can cover in a single video, but essentially we just need to concentrate on this training part and doing the customization on the input states and everything. So that is the main functions we have to focus on. and try to save your models like frequently, like this. After 20,000 episodes, save your model, so it'll be easier to stop and get your trained model in between. Like if you are running for more than 1 lakh or 10 lakh episodes, means it's better to test your model in between. So that's why just save your model and have a backup. And yeah, that's it guys. If you have any queries related to this code structure, or how to run this reinforcement learning for any other projects, please leave a comment below. I will definitely help you. And apart from that, you can get this code from my GitHub repo. If you like this video, hit the like button and don't forget to subscribe the channel for future videos. Stay tuned for the next video.